In this video, we're going to look at the macroscopic consequences of Ostwald ripening on our consideration of gas storage underground. In the previous video, we showed that at the pore scale, there can be significant rearrangement of the gas within days to months. So in most natural situations where the gas is there for months to millennia, we expect Ostwald ripening to be significant. But we've only shown that at the pore scale. So what does it mean in terms of macroscopic properties? Well, let's start straight away by looking at capillary pressure. So imagine this is my capillary pressure, and I'm going to step through what that means physically as well. So this is a capillary pressure of 0. We're going to assume that the gas is the non-wetting phase. The aqueous phase is wetting, so the capillary pressure is always going to be positive. And this is going to be the saturation of the wetting phase, the aqueous phase, water. This is going to be 0. This is going to be 1. So imagine initial gas injection into the pore space. That's a primary drainage process. That will be when we're putting hydrogen underground for the first time, natural gas storage again, putting the gas underground, CO2 storage again, injecting the CO2. And we're going to assume that we inject to quite a high capillary pressure, so we get to what we call an initial or water saturation that's close to an irreducible value. So this is going to be a small value like this, and we're going to get a capillary pressure function that looks like this. And this is a primary drainage, right? So this is drainage. Now, I'm going to consider two scenarios. The first is what you do in a normal laboratory experiment. In a normal laboratory experiment, you will inject now back the aqueous phase, the wetting phase. You can either do it in steady state at a series of increments, or you simply inject it in an unsteady state experiment. However, those experiments are not waiting months at every stage. So we're going to assume that these experiments are done sufficiently quickly that in fact Ostwald ripening does not have an effect. Or you're not using gases, but you're, for instance, using an oil water system, or maybe even a mercury vacuum system, where Ostwald ripening is not going to be effective. In an oil water system, there's negligible dissolution of the oil in water. And of course, the oil is a lot denser, so there are a lot more moles you need to move around anyway. So let's imagine a laboratory experiment that does not have Ostwald ripening. So in that case, this will be a classic imbibition experiment like this, and you will get a residual saturation here, S2R. That's the residual saturation. And until now, that's essentially what people have done and used. You do primary drainage, you do a secondary imbibition experiment. And that's an experiment that may take a few weeks, it may take a few days, but essentially you have not allowed enough time for Ostwald ripening to reach true equilibrium. So what happens if you do? And what is the process? So now let's think about this carefully. So imagine we have originally well-connected gas through the pore space. So here's the gas phase. It's going to be well connected. It's got lots of loops. There may be some water here, but it's well connected. And now water is going to come in, say, from the bottom here. Initially, you will trap some ganglia, but they'll tend to be small ganglia, and you trap at quite a high capillary pressure, so early on in the displacement. So you're going to have some ganglia, and they will tend to be small, and they will have been trapped at a high capillary pressure, okay? But now, as there's more and more displacement, there'll be a sort of tenuous connected phase here of the gas. Think about the final displacement, and it will be a snap-off event. For those of you who've seen the early videos, be a snap-off event that finally disconnects the gas. Sort of by definition, the remaining clusters either side of that event are actually going to be big, and they're going to have been trapped right at the lowest capillary pressure. So let's imagine we got a big trapped ganglion here, and there was that snap off, right? Like this, and then there'll be other ganglia of different size like this. Okay, so that's what happens in a traditional experiment. You've trapped these ganglia at high capillary pressure, and the larger ones in general will have been trapped at a lower capillary pressure. So the Ostwald ripening process, just as I showed in the previous video, you'd expect these ganglia to shrink, might even disappear completely, and these ones to grow. So that's exactly what you see experimentally. So experimentally, there is a tendency for there to be a transport of material, dissolved material, goes from here to here. These ganglia can even reconnect, and these ganglia sometimes can disappear completely. So there is a tendency essentially to reconnect. So if you trap and reconnect, you see these drainage type displacements, and you actually have a more connected gas. Indeed, the gas can be connected and can now flow. So what is the correct model of displacement? What happens if we assume, as actually happens in the deep subsurface, that these processes are occurring very slowly? So what happens is this. You've got events like this. Imagine this is the remaining trapped cluster. Sorry, the remaining connected cluster. It's just about to be trapped at a low capillary pressure. But hang on, there may be displacement events that could occur, because these are at a high capillary pressure, displacement events that could occur within these trapped ganglia. Now, normally you say, well, they can't occur because they're trapped, right? The gas is surrounded by water. Where can the gas go? But if you've allowed enough time for Ostwald ripening, for transport in the aqueous phase, you will allow displacement. So if we are at true equilibrium with Ostwald ripening, at every step in the capillary pressure, all of the ganglia, including the trapped ones, are at the same capillary pressure. And if the capillary pressure goes down and there's a trapped ganglion where there could be a displacement, that is, water could move in, it does. And where does the gas go? The gas is transported in the aqueous phase. So for those of you who see my previous videos on displacement processes, secondary imbibition I've described as percolation with trapping. So essentially, you're filling with water pores and throats that were occupied by gas, largely in order of size. It's in order of capillary pressure, strictly speaking, but once trapped, it's trapped, nothing else happens. That's true if it's all water. Not such a good approximation if it's a gas-water system in the subsurface with a slow displacement. Instead, the correct model is actually percolation without trapping. You just allow any event that's allowed to happen, and the trapping doesn't matter because the gas can escape in the aqueous phase. So what you have as the equilibrium model is something that looks similar, but as you begin to trap, you can displace additional material. So this is with Ostwald ripening. And this is percolation without trap. So it's an easy model. You might say, whoa, just a minute, there's a problem here because you said it's without trapping, so eventually everything goes. No, there is a subtlety. Even with percolation without trapping, that is, you allow any displacement, eventually everything gets trapped. And once everything gets trapped, you can no longer impose an external capillary pressure. See, when the two phases are connected, both phases are connected, I can increase the pressure in the water or decrease the pressure in the gas, and I'm imposing a capillary pressure. Once the gas is all trapped, actually nothing more happens because I cannot impose a capillary pressure that would allow the rest of the gas to dissolve. I can do that, I can just keep injecting water and eventually the gas dissolves, but as a displacement process, I can't do that. So in fact, you do trap within the pore space, but you trap less. So this is the residual, say, with trapping, okay? And this is the residual with Ostwald ripening, okay? Maybe you call it Ost. And what we find, and this is empirical, so we can model this process, what we find is that with percolation without trapping, you have about 20-25% less trapping. So it's 20-25% lower residual gas saturation. Okay. And then how do you incorporate this in your models? Well, actually, it's quite easy. You do a scaling. Essentially, you scale the measured capillary pressure, so what you measured in the lab without Ostwald ripening, you can predict with percolation without trapping with a model what the decrease might be, and you just scale the capillary pressures. So you assume that the capillary pressure can be written as a function of an effective saturation, and this normalization is this. It's S1 minus the initial, so it's a value that goes between 0 and 1, and then this is 1 minus SWI minus SGR. And instead of water, you can, if that's specific to water, if we're doing it more generally, this will be just the water saturation. This is water, and this will be phase 2. So it's either gas or water. You can choose whichever subscripts you like. This SE goes between 0 and 1. And what you do is you measure this with this larger gas saturation, and then you rescale with a lower gas saturation, which is percolation without trapping. Now, just 2 more things to note. What you might also consider doing is an experiment where you do the experiment quickly, you then look at the ganglia rearrange, and then you see how much more you can displace because the ganglia do reconnect. Problem is, turns out to be really subtle because this process involves both imbibition, because some of the ganglia shrink, and drainage. And because of capillary pressure hysteresis, if I start here and then allow the saturation to be the same, I don't necessarily go up to exactly where percolation without trapping would be. Because percolation without trapping is all imbibition events. I'm not actually forcing anything in drainage. So that's the first subtlety. And it then makes this experimentally extremely difficult to reproduce. In the laboratory, we can image this, we can see the rearrangement of the ganglia, everything checks out with the theory, we see this increased connectivity, we know the residual is lower, but it's actually quite difficult to quantify it. The second thing, and maybe the most subtle thing, is people are going to say, hang on, this is all at the millimetre scale. Doesn't make any difference at the large scale, all right, because we're looking at hundreds of meters, maybe kilometers. This is the subtlety. What happens with Ostwald ripening is it does allow disconnected ganglia to reconnect. Once they're reconnected, they can flow in their own phase, described by a capillary pressure and a relative permeability that is finite. So it is wrong to say, but we're looking at 100 meters, put L equals 100 meters in that equation, Martin, and you're going to get billions of years, and so it's irrelevant. No. At the millimeter scale, things can reconnect, it can rearrange. And then that means that the gas is connected and has a finite relative permeability, which if you put in your flow models, will allow that gas to be moved. So the reality is, at the small scale, yes, it does make a difference, and you do see a lower residual saturation and essentially less hysteresis. There's less difference between drainage and imbibition. So it's still very much an open question how to quantify it, You can essentially estimate this using pore-scale modeling that is validated against a measurement you've done at a fast flow rate, and then extrapolate it to what you think might happen in the field where you've got time for this Ostwald ripening process to occur. But overall, absolutely fascinating. You allow for some transport in the aqueous phase, and you find a whole host of new phenomena emerge when you try to describe multi-phase flow in porous media. So that concludes my discussion of Ostwald ripening. Thank you very much.